Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and scale. This will be done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. More information on the G-PST can be found at www.globalpst.org. ESIG serves as the lead of Pillar 1, and as such would like to welcome you to our monthly joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and will focus on the research agenda and research questions being addressed in Pillar 1. Topics will be presented by both the founding system operators and other advanced system operators active in Pillar 1, members of industry and academia participating in the activities of the Research Agenda Group, and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST will also be provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at www.esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're going to be using the Slido platform at slido.com. We will not be using WebEx for questions. You need to open a browser window, go to slido.com, and enter ESIG10, ESIG10, as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar consists of a talk on grid-forming inverters and power export stability. Based on the number of registrations, it looks like this is a very popular topic. In fact, I'm calling this Inverter-Based Resource Week at ESIG because we have 3 IBR events this week, of which this is the second. Today's webinar will feature Nick Miller of HickoryLedge and Matt Richwine of Telos Energy. Nick recently retired from GE, where he spent a long and illustrious career in power engineering and renewable energy. Nick is active in both G-PST and ESIG grid-forming inverter activities and is well known to many of you. Matt, also ex-GE, is a founding partner of Telos Energy and is passionate about power system engineering and renewable energy as well. He is a familiar face at ESIG and has a special interest in system stability. I feel very fortunate to have Nick and Matt here with us today. They're both good friends, and it's a pleasure working with them. The webinar today will focus on the stability challenges of getting the power from large areas of high-quality wind and solar resources across AC transmission to load centers. It will examine the performance of emerging grid-forming inverter technology relative to grid-following inverters and synchronous machines. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG10 to ask your questions. And without any further ado, let's go ahead and get started. Nick, I'll now turn it over to you.
All right, thanks for the introduction, Charlie, and welcome everybody. Lots of lots of friends on this call, I think. And I'll start off. Matt and I are going to tag team on this. So I'd like to, I'll get us wound up and then hand it over to Matt. Also, before I go any further, I'd like to acknowledge that Matt and I are doing this work under the sponsorship of Grid Lab, and we appreciate Rick O'Connell funding this relatively small, but we hope you'll find exciting effort here. So with that, Matt, let's go on. So I'll start and start to walk you through, what we're trying to do, and frankly, what we're not trying to do. This is a limited, I don't want to say limited so much as focused exercise, and I think you'll find it accessible. Those of you that are in the audience that are deeply immersed in this topic may find yourself chafing at some of the narrowness of this, but that's okay, and we'll have a vigorous chat about what we think we've learned when we get to the end. So we'll go through the theories and et cetera. So yeah, let's go ahead and stay on this context slide. So the genesis of this work was, frankly, Matt and I chafing at the bit over some of the uncertainties and belief that, gee, aren't some of these problems that we're talking about solvable with grid forming inverters? And of course, we aren't in the least sense alone in that. But we zeroed in on this particular topic. This is partly driven by the frankly superior work done by MISO, by Jordan's team on the RIA, where they identified a variety of grid-related issues related to getting the power out from getting the wind power out from the high plains. You will recognize this problem. It recurs in the Western interconnection. It occurs in Texas. So these are questions of grid strength and power transfer and making the voltage healthy. It fits nicely in this pyramid, which of course is an eye chart here, but we wanted to put it in to provide perspective. This is the NREL grid forming inverter roadmap. There's lots of, this is a rich space, but the second from the top slice, which is bearing down on this as we speak, is the question of getting power into the bulk system. So let's go on to the next slide, Matt. The question of getting power out of these resource-rich areas is really burning, right? Those of you who have been paying attention, we just have looked at the E-Cig white paper on how to get tens of gigawatts of new power transfer capability, a mix of AC and DC. Bill, we are talking at a national level about investment in infrastructure that is measured with an almost uncountable number of zeros to the left of the dollar sign. So we are not trying to answer everything here. We are looking at the stability issue of getting the power out. And frankly, we are specifically driven here to identify ways in which transmission infrastructure and probably new transmission infrastructure will be absolutely maximized. We simply, as a country and as society, don't have the luxury of building transmission that's underused, and that's the focus of it. So what is it that's limiting the transfer in this world of IBRs? What can GFM do and not do to raise those limits? And how is a team in a real world environment supposed to start to wrestle with the arms and legs of this problem? What should you be looking for in planning studies? And what what do we need to do with the tools? So we're starting with something pretty simple so that we don't get lost, frankly, in the woods. We're trying to get a picture of the forest here. So with that, I'm going to turn it over to Matt to lay out how we tackle this. So Matt, go ahead.
Great, thanks, Nick. So wanted to get everyone on the same page here with a brief overview of the technologies that we really have in focus. And brief really being the operative word here. We're going to spend just one slide on here. We could spend a workshop on these topics. And in fact, there was a great session through E-Cig and a great workshop yesterday that covered a lot of this in more depth. So I'd encourage you to go and check that out as well. But the three technologies we wanted to look at are synchronous machines, grid following inverters, which we're abbreviating GFL here and will be going forward, and grid forming inverters or GFM. And we wanted to look at, and here I just wanted to highlight three aspects of each of these that we think is important. One is behavior. The second is about the energy stored in each of these resources, typically. And the third is about the ability to release that energy, or kind of the power capability of each of these resources. So beginning with synchronous machines on the left, the behavior we tend to think of as electrical engineers, as we model them as a voltage source. And they have an inherent response that is defined by physics. And if you subject a synchronous machine to a disturbance, it is fairly predictable based on the size and dimensions of the machine what will happen. From a stored energy standpoint, the synchronous machine stores energy in two different ways. There is a rotating mass of the spinning rotor and the connected drivetrain that has energy, kinetic energy in it. And then there's the magnetic field energy of the flux in the core. This level of energy in the synchronous machine, it's just a ballpark. It's relatively small, right? It's a couple seconds at rated power worth of energy. However, synchronous machines have the ability to release this energy quite quickly. Multiples of their current rating is what you can see in peaks. And that's something that we've grown accustomed to and frankly been relying on to operate the system and for the stability of the grid, and that is that is dominated by physics. And one of the aspects, I mean, everything here is dominated by physics. We're ultimately subject to that constraint, but of course the synchronous machine, it's a copper and steel machine, and so you have a lot of overload capability in those types of materials. Now, when we transition to looking at the inverters, starting with the grid following inverters. So the behavior, we tend to model like a current source. And I think of this as a sense, then respond type of behavior. And it is software defined, as we're well aware. The stored energy is conventionally very small and much smaller than when compared with synchronous machines. Particularly with PV and wind, except for batteries. Batteries have kind of hours of rated power of energy available, but they are limited in their ability to release energy, typically 1 to 1.5 times the current rating. And that is because unlike the synchronous machine, the copper and steel machine, these are all of the current, all of the power is going through the silicon devices, the power electronics, and they have a very limited thermal capability, which means that you cannot pound these devices with high levels of current for very long times at all. In fact, very, very short periods of time. They're very sensitive to this. Similarly, on the grid forming inverters, there is the energy and power capability is shared, is similar. They have a limited ability to release the energy quickly. They generally have, at least in the case of PV only and wind turbines, they have relatively short energy storage in them. Batteries, of course, being much longer. But the real distinction here is on the behavior. And it behaves like a voltage source, like a synchronous machine, or it's intended to, what I'm calling inherent like. But this software, and we'll talk more about what that means, but the response is software defined. Now, one comment before we leave this slide, these buckets and these lines, they're porous, right? This is really not a discrete and bright line delineation between these types of technologies. It's really a continuum. And as I think Professor Green mentioned in the workshop yesterday, you know, you could think of these as there's a lot of gray area in between here. And I think we're trying to understand the different characteristics and space here to work with. So for now, we'll leave it at that, and we'll come back with a little bit more detail. So our working theory, and again, this is, you know, we're on a journey here and we don't have it all sorted out, but we think we're making some headway. How we're thinking about this is we're going to start with what do we know, what do we have experience with? Synchronous machines, grid following inverters, you know, many gigawatts deployed, many years of experience here. And so let's start with what we know and go from there. And to do that, we've decided to characterize these things. We're thinking about these in two different time frames, a very short time frame and a longer time frame, and drawn a line in the sand pretty arbitrarily at 100 milliseconds. But for the sake of thinking about it, that's where we're starting. So if you look at on this graph on the right here, we've got kind of that time, dividing that time frame. And on the left, you have the potential advantages for stability. So how would these resources that we started talking about, how are they going to play in terms of stability on the system? The synchronous machines, what we tend to see is in the very short time frames, they have an inherent open loop behavior that is generally stable. And there are some advantages from stability for that type of characteristic. And so we see the blue line on the left for short time frames goes up. There are some advantages we see there. However, on the other end of the spectrum for synchronous machines, the longer time frames, we know that they have those electromechanical modes that they are subject to. It's kind of the baggage that comes with that technology. It's always been there, and generally we've been able to manage it, but it's there. And we'll see exactly what I'm talking about there in a few slides. But that tends to limit us in terms of angular stability, first swing stability, and some other challenges that we have to manage in terms of keeping the system held together, especially when it starts moving due to a big disturbance. On the grid following inverter, we see kind of a complementary nature of this in terms of on the very short time frames. So the closed loop controls are challenged to maintain stability for very short time frames. Again, this goes back to that see, that sense, then respond. It takes time to sense, and it takes time to respond and to do the right thing. And when everything is moving and the times are very short, it can be very difficult to sense it correctly and then do the thing that you intend to do. That makes the stability challenge a bit harder in those short time periods. As an industry, we've come a long way. We've been able to push that, I think, farther and farther and achieve stability in places where 10 years ago we certainly couldn't with that technology. And I would say it's not done evolving yet. Right, but then we see on the other side for the longer time frames, the grid following inverters tend to have some advantages of stability in that they don't have the baggage of the electromechanical modes with them. And they tend to be kind of very resilient in that when the grid is, let's say, moving rapidly after a disturbance, they're always trying to get back and synchronize and be stable and contribute and support the grid. So this is the way we've been thinking about it. And the way we're analyzing it is, again, with a simple model. And starting on the left here, the sending end, the devices in the inverters in green and the synchronous machine in blue, we're looking at the different resources, in most cases, one at a time, the GFL, GFM, and synchronous machine. They're connected to a high voltage transmission system, which I'm representing in blue here, as a couple lines in series, and then they're transporting their power to the receiving end, which is comprised of modeled as a large synchronous machine, a lot of pretty good amount of inertia and some local load. And so the power is going from left to right. And some of the things that we're going to be testing and checking are supporting this power path along, supporting that transmission along the way with synchronous machine, and particularly for this talk, talking about what another synchronous machine or synchronous condenser tends to do along the way. One of the reasons that we've underlined this approach is that we have a working theory that the midpoint of the transmission corridor, the power path, tends to be soft. It tends to be where the voltage, if you're over your surge impedance loading, the voltage can get weaker or lower. And our hypothesis being that that is a good place to provide some support. So that is one of the things that we're looking to understand a little bit better. And so, Nick, on the system stability side, why don't you take it away?
All righty. So it wouldn't be a complete talk from Matt and I without a pile of wiggles and a bit of an eye chart. So nevertheless, we thought it was useful for you to see this matrix of cases. So let me tell you what you're looking at before you try to squint at the wiggles inside. So the three columns from left to right are the system getting, are our test system, they're getting progressively weaker, which is, we accomplished making it weaker by making those EHV AC transmission lines longer. All right. So we chose, Matt and I chose a little language here, trying to be careful. The strongest grid we looked at, that we're reporting on this chart, I should say, is still relatively weak, and a few years ago would have been considered extremely weak for grid following inverters. So it's a short circuit ratio of 2.2. The center column is what we've called the marginal grid, and it's marginal because the stability of our available technologies are marginal. And that's got a short circuit ratio of 1.4. And then we've gone to a weak grid of a short circuit ratio of 1.1. And we went quite a bit below that, as you'll see with the grid, a bit below that, I should say, with grid forming inverters. So the, and then from the rows are labeled on the left. So from the top row is our grid following inverter. The center row is synchronous generator, and the bottom row is our grid forming inverter. I think Matt said, but I just want to drive this again. You know, these are good models. These are representative of the current state of the art, we believe. But the notion that it's a monolithic GFL does X, GFM does Y, we want to very strongly distance ourselves from you taking that away from this. But these are good representations. These are based on commercial equipment. So, and, you know, we trust them. They're well vetted. So without looking deeply at the wiggles, the outline of these of the boxes are representative of our sort of stoplight approach here. So the green cases are stable. You'll notice that the synchronous generator has got kind of crappy damping. We didn't mess around too much with this with the power system stabilizer. That is not the damping is not the limiting phenomena in our decision of whether it's stable or not. The yellow ones, two cases in that middle, are stable in the sense that they actually make it, but they are violations of NERC and WEC voltage swings. So those are fails from a system performance point of view, but it's illustrative to think that you know, if the system comes back, if it gets through a wiggle, it's somewhere not acceptable, but neither is it a complete fail. And then on the right, the two red boxes are actual fails where the generation trips because it didn't survive. So we were building on this space. So with that, let's look on to a broader behavior. Oh, sorry, Matt, go back. I did have another point to make on that slide. That is, you know, Matt made comment about the currents and the ratings of these equipment. And we're going to make a few comments about that at various times in this. But To get this stable behavior across the bottom with the grid forming inverter did not, I want to emphasize that, did not require us to alter the current rating. All right, so we went to great pains to make the GFL versus GFM apples to apples. And this good stability behavior for this event, for this setup, we're putting qualifications on it, does not require beefing up the current carrying capability beyond something that you would expect for this class of equipment. We think that's pretty important. That doesn't say we're saying don't worry about the current. We're saying that it doesn't look like you need a lot of current capability to get this good stability behavior. Pretty important finding. Okay, let's go on to the next slide. Okay, so this is a bit of an eye chart. We were inspired by John O's world-changing J curves and thought we would try to get some visuals here that you could take away without being buried in wiggles and numbers. And on the left is a stability regime that's reflected in those outlines of the previous slides. And you see a bunch of dots. Those are cases that were run for that primary clearing time of 100 milliseconds. And the y-axis, I know it's very small, but the y-axis is the grid strength, the short circuit ratio. So as you would expect, as the grid gets stronger, the cases are more stable. And as we saw in those wiggles, somewhere around 1.4 short circuit ratio, that GFL is marginal. Around 1.1, it fails. And as it gets even lower than that, it completely fails. Okay, we kind of expected that. What you may not expect, and we think this is a significant observation, it's probably not the first, we aren't the first ones to make it, is that the duration of the fault, okay, that's the x-axis in these, all three of these sets of plots, isn't very important for the IBRs. The energy that isn't delivered during the fault has very little impact on the recovery, and we see almost no impact on the stability as we move across to longer duration faults. So that tells you that we're really focused on the network effects and not on the energy involved during the fault. So we make the fault longer, it's essentially the same stability. That is really contrary to your experience, to those of you that do stability, and look at the middle plot, which will be much more familiar to you. You know that as the faults get longer, the synchronous machines are less stable. So as we're moving to the right, the unstable region, the ability to have sufficient synchronizing strength to pull the synchronous machine back in once the fault is cleared is a really important piece of stability analysis. And you've all, those that live in that world on the call here, have recognized that. But it is fundamentally different than what we're seeing with the inverter-based resources. So in this primary clearing regime for the system we've set up, the behavior, the stability limits for the GFL and the synchronous machines were very similar. We're not saying that that's a general truth. We would expect them to be in the same neighborhood. And now, if you look on the right, we're finding that the GFM, as we're modeling it, is substantially more stable, and it's good down to a short circuit ratio of somewhere maybe in the neighborhood of 0.8 or 0.9, which is kind of the Ohm's law limit. And again, we see very little impact of the duration of the fault, and the difference between stable and seriously unstable, that is the thickness of the yellow trace on this figure, is thin. The system goes from working to not working, and we thought that that was significant. So in the end, you see we've reproduced Matt's hypothesis figure at the bottom. We think that this grid forming has kind of successfully captured the good, the best of both worlds. Many questions remain, right? We got a nice parameter exercise in space, we're the first to admit that this isn't even remotely exhaustive. So Matt, let's go on to the next one. Oh, and I'm going to turn it back to you, in fact.
Great. So yeah, we wanted to do some tests, basically some experiments to at the equipment level to gain some insight into why are we getting the responses and that behavior that Nick just showed, and what are some of the comparisons and contrasts among those three different technologies. And so to do that, we've applied some step tests to the units. So in this one line diagram here on the right, we're looking at each resource one at a time and its related electrical balance of plant equipment connected to a voltage source where we're manipulating the voltage source. And how we're manipulating it is we're applying a step test of just voltage magnitude, and we're going to check the response. And that's an example of which is we're showing in this yellow trace just below, applying, in this case, we're looking at 6% voltage magnitude steps. In another case, another test case, we're going to look at voltage phase angle steps of 5 degrees. And we'll look at them in a few directions. And by the idea here is to try to isolate some of the characteristics and exercise different parts of each of these resources in a way that is repeatable and provides some insight. Now, you may say, a fault and a line switching event and other, loss of generation, this is not directly those events, right? But those types of real world events have some step components as part of them. And so we're really just trying to tease out and understand this behavior a little bit more in a repeatable way. So looking at first the voltage magnitude step responses. And so on the left, we're going to compare first the inverters, the GFM and the GFL to the voltage step response. So in all cases, first, you can see here that for a voltage magnitude step up, and granted where voltage phase angle did not change appreciably, the intent was it did not change. What you see is the reactive power response, or of all of the devices goes down. And so this is to be expected. This is a corrective action. But what we really wanted to zoom in here is on the dynamics, and particularly in the short time frame after the event. And so you can see that the grid forming inverter, the reactive power response goes down very quickly, basically immediately, and then stabilizes. In contrast, the grid following inverter has kind of maybe a little bit of a wiggle at the very beginning, but then it has this gradual dynamic decay down to the new value. And the scale, I understand this is hard to read. This is about 2 seconds of simulation time, or about 200 milliseconds per division. So we can see that there is a pretty substantial difference right after, in about the first half a second after this event. Now, if we shift and look over at the grid forming versus the synchronous machine on the right, you see a couple things. One, they both go down as we expect. Two, the dynamic behavior is actually quite similar. They both immediately jump down to a lower level. And then three, the steady state values are different. And we can talk a little bit more about that. That's kind of indicative of the effort, the corrective effort that each resource is able to apply kind of more consistently. So that is, one of the things that really jumped out here is that we can see in comparison and contrast, the GFM in these short time frames has a dynamic behavior that is more similar to a synchronous machine than it is to a grid following inverter. I think that is, and to me, that is the evidence of grid strengthening behavior, that grid strength that we conventionally have relied on today from synchronous machines is possible to come from the grid forming inverters because of this type of behavior. Now it doesn't, this is not to say they're a one-to-one substitute, and we'll talk a little bit more about that. One other quick comment, just so that it's not a distraction. You'll see that for folks that maybe are not used to looking at plots like this in these time frames, there's a lot of wiggles going on at the fundamental, at the power frequency, 60 hertz. They're small. These are things that are generally expected due to slight offsets of DC or slight asymmetries. That is an aspect that shows up in EMT modeling, where you're looking at these things in very fine detail. And one of the other things that, a lot of folks may say, well, gee, I've run PSCAD simulations and maybe have not seen this. There's some filtering applied to some of these that we addressed explicitly, where we wanted to make sure that we were not filtering out too much and obscuring some of the fast dynamics. So that's a quick reason why some of those wiggles are showing up here. Okay, moving on to the phase angle step responses. So first we're going to look at a negative phase jump, phase angle jump. And again, on the grid forming versus the grid following inverters, what you can see is that active power is from the grid forming inverter is reduced quickly, and then it moves back to its pre-fault state, its pre-fault level in about 200 milliseconds. In contrast, the dynamics of the GFL are quite a bit different. There's a disturbance of sorts, but in general, the power doesn't change much, and it kind of cruises through the event because it's intending to regulate power to the extent that it can. When we look at the grid forming versus the synchronous machine behavior, we see, again, the same stimulus applied to each resource. We see in the first 200 milliseconds, again, very similar corrective dynamics from the synchronous machine and from the GFM, or in that first 1 or 200 milliseconds. But what we also notice here is significant electromechanical modes evident from the synchronous machine. You can see the large oscillations that are slightly damped in this case. This is that baggage that comes with the electrical modes that we were describing earlier. And what's very apparent is that from the GFM, we don't see that. It's software defined, it's not physics defined. And so if you don't include that mode, you're not constrained by physics to experience it. And so what we see is, I think there are some significant implications for this in terms of damping and potential stability aspects on the grid. One other note to call out here is the energy. So in the light blue triangle, this is the transient energy that is taking place during the event. And we've kind of put a rough quantification on that, 25 kilojoules per megawatt. And we'll talk a little bit more about the implications of that energy. And in particular, when we were talking about first comparing the three resources, we talked about the energy storage, right? And so to put that in context of, what's a little bit of energy storage versus what's a lot, I think the reference point for that is the transient energy from some of these events. So I wanted to highlight that, but bear with us. We're going to come back to that in a little bit more detail. But there is evidence here of a true inertial response from GFM in the way we know it from synchronous machines, but without some of the electromechanical mode baggage. Okay, so now let's look at, and I'm going to try to pick up the pace a little bit here. Nick, jump in here if there's anything that I'm glossing over too quickly. We wanted to look at the phase jump event. We wanted to look at a bigger event in each direction. And so, and particularly zooming in on the grid forming versus the synchronous machine. So on the left, again, the same type of event, but just bigger, a bigger whack. And what you can see in the direction of where power is reducing, you see similar behavior to what we saw beforehand. What we've expected, just the numbers get a little bit bigger, the power reduction is bigger, the electromechanical mode, the swings are bigger. Where it starts to get interesting is on the right, where we look at the same phase jump but in the opposite direction, such that the response that we would expect would be an increase in active power transiently. And you can see the synchronous machine in the blue line does that. And we're talking, the scale here is actually the power immediately after the event nearly doubles from what it was doing, which is also well over the rating of the machine that was modeled. That's something that we expect. They have a high capability in that, a high ability to take that rotating kinetic energy from the rotor and move it to the grid. They have a great ability to do that. However, on the grid forming side, where you have the power electronics in between, what you can see is, and what we know and what we expect is that at some point, they're going to hit a limit. All resources have limits, so this is not expected, but the behavior at the limit may vary, and particularly when it's software defined. And so what we wanted to show here is that, you know, in general, we're seeing very promising aspects from grid forming technology, but we don't want to paint too rosy of a picture necessarily either, and that there is a lot more that we need to understand, and particularly the behavior at the limit, not because we intend to operate at the limit or certainly not over the limit, but because we feel it's important to know what happens when you get to the limit, such that the results are acceptable, that you don't have a massive failure. And so this is one of the things that we wanted to share here that we're still digging into and needs to be better understood. Okay, so Nick, back to you on about.
All right.
Yep.
Thanks, Matt. This is so this is one of my favorite topics, and will be near and dear to at least a few people on the call. And you've heard about this from other speakers. You heard about it yesterday from Babak, and it's an issue in ERCOT. So in this case, we have looked to strengthen the grid at the midpoint, and Matt and I have done lots of parametric work on size, inertial, location. But this is a relatively simple exercise in putting a condenser amidships to try to reinforce the system. And indeed, so this is a case here with the GFL and the condenser in which we were right at the edge. This is actually, again, one of those yellow traces because the voltage swing is too violent. So it's a fail from a voltage swing, but the system does get through it. And we picked this one to talk from because it illustrates what we believe to be an important point for planners and people doing work to be aware of. And what you see here is the top is the voltage swings out at the IBR, and they're pretty ugly, and they're swinging at about 1.3 hertz. We've got that labeled in gold. The lower trace, the blue trace, is the active power swings of the synchronous condenser. And those are dominated by, as Matt keeps saying, the baggage, which we kind of like for the condenser. And they are distinctly different modes, but there is cross coupling. So the top one is driven by the control of the GFL. If you had a different control in GFL, you would almost certainly get a different behavior. Maybe that could be stabilized somewhat, but remember, this is a very weak system and is characteristic of running at about the ragged edge of GFL stability. The addition of a synchronous condenser changes that short circuit ratio in a direction that's kind of consistent. It's not quite as effective as making the systemic short circuit ratio better. And I know there's a few people on the call that are going to be wincing at us simplifying the system strength to only short circuit ratio. Yeah, we get it. There's a lot of other metrics in terms of the natural frequency, et cetera, but short circuit ratio is still a pretty good proxy for system strength. So two different modes. The synchronous condenser is being exacerbated and interacting with the IBR, but it is the dominant source of that slow mode and vice versa. So if we go on to the next slide, this is our apples to apples comparison, all of the things being equal, the same synchronous condenser. And the lower, let's talk about the lower trace. First of all, we didn't alter the natural frequency of that synchronous condenser against the rest of the system. It's still at about 0.9 hertz. Those swings are about half as much because they are not interacting anywhere near as much as with the inverter with the inverter. So you see the inverter does have some swings. The system is still highly stressed even for the GFM, although as you can see, that's an acceptable case. The voltage swing is tolerable, and indeed it's tolerable for even more stress than this. So we think you got to be wary of these different modes. All the stuff related to the GFM, all the red trace stuff is control. So yesterday, those of you that were listening heard Andrew Isaacs talk about the fact that the controls introduce a whole bunch of stuff that are outside of our institutional experience base to some appreciable extent. You recognize the swings on that, the blue swings. You know they're there, and you say, why didn't you guys put a better power system stabilizer on? You know that putting a stabilizer on a condenser is pretty tricky to get right. We didn't fuss over that too much. It's at least positively damped. So we think diagnostically, as you go forward with GFM, this might be another good piece of good news. The system is more stable and the modes are more distinct. So when you're trying to do diagnostics and make the system work better, there's a lot less crosstalk in the modes. So we think that's kind of a cool and probably a fairly generalizable result. Although remember, we're looking at this pretty narrowly. Okay, so I think that was everything we wanted to say about that, and we're on to our summary of findings here, and Matt and I are going to go back and forth. You know, we see from this kind of topology, which we still think, even though it's very simple, is very relevant to a lot of the money-making questions. To my early emphatic statement at the beginning, we have to get as much power as we can on the existing and new transmission, and that is going to pay the rent, all right, at every level. We're seeing relatively simpler stability limits. We see better stability limits with more benign swings with the grid forming inverters. We see that that the synchronous machines, not surprisingly, are quite sensitive to fault duration. You already knew that, and it's not for the inverter-based resources. So some of the old metrics like critical clearing time might not be the way we want to go. We're looking for some other ones. And Matt, why don't you pick up the other points in here?
Great. Yeah, I think, you know, and then when we zoom in on some of the behaviors of each of the resources, I think we see that the GFM does show some similar characteristics to the synchronous machines. And I would say the similarity to some of the desirable characteristics of synchronous machines, which I think is the intention, while some of the other characteristics of the machines being the mode, the swinging behavior, doesn't necessarily need to be there, and you know, is desirable that it's not there. And in this particular case, we found that it was not there. But we do also need to be aware and have our eyes open that the behavior and limit is going to be different, and because the hardware of these machines is of these different resources of inverters versus synchronous machines is quite different. But that said, you know, to underscore a point Nick made earlier, you know, we often associate very high fault currents with synchronous machines, and yes, there are some important aspects about the way the protection systems have grown up and been designed and are implemented today that expect and rely on this and that predictability. That's something that we want to acknowledge. It's very important, but it was not front and center here. And it's something that we've taken the approach where that needs to be considered, but should be considered separately. A couple other big takeaways that we found from dipping our toe in this is that, as we known or as we suspected, all technologies are sensitive to grid strength. We do have some evidence that the transmission network tends to be softer in the middle, and that if you have a choice of where to provide some support for the grid, often the middle can be a good place to provide some support to the transmission network. But there's a slew of asterisks on that, particularly when you're talking about synchronous condenser mitigations. There is a lot of complexity there. The location matters, where the faults occur with respect to the different resources, the modes of the system. It can all introduce a lot of different dynamics that is something to be aware of. So, as we've mentioned, this is a journey. There's a lot more to come here. We've started relatively narrowly or focused, as Nick would say, in terms of looking at a simple topology and trying to understand, where can we understand the characteristics and the performance of these behaviors in a way that we can then use to understand larger and more realistic systems. So I think on that, Nick, is there anything else you wanted to add?
No, I think we could talk about this a lot, but let's use our last 10 minutes to take some questions. I think we got the critical pieces out on the table here.
Okay, thanks for that, Nick and Matt. We got a lot of questions here. And I think I'm going to look at the top of the Slido because there's some pretty interesting ones up there. Deepak had a couple. Are the grid forming and grid following IBRs considered in this study battery energy storage systems with a stiff DC bus? And then a follow-up question. In both the GFL and GFM IBRs, could you touch upon what is their current injection scheme during the fault?
Yeah, so on the GFL and GFM, yes, these are battery resources. And so, yeah, you mentioned the stiff DC bus. I think there's a lot of discussion yesterday in terms of, where that differs in terms of applying to PV technologies and wind technologies. So we can maybe touch on that a little bit, but in short, yeah, these models did consider battery energy storage behind the inverter. In terms of the injection behind the, or in terms of the current injection mode, so the GFL in particular was operating in a Q priority mode with a kind of a relatively fast voltage regulation, terminal voltage regulation. And then layered into all of this was also a plant controller. So the intent to be, the idea being to model what is kind of as realistic and state of the art as many of the installations are today.
Okay, and I think we'll move into the follow-up question from Mark Ahlstrom, building on the questions from Deepak and yesterday's session as well. Yesterday's panel said that grid forming inverters for battery storage were available today. We talked about the SMA inverters. Are they commercially available, and would you recommend using them? Well, if that's not a loaded question.
Yeah. Let Matt go, and then I want to add to that.
I was just going to let you go, Nick.
Yeah. No, I could. Yeah, let me just go. Right. Yeah. The short answer, the answer to your question is yes. I think Andrew Isaacs said it well. Why are we building battery? I have a real worry about us building battery energy storage systems today that don't have GFM. Quite honestly, the focus of this work is not getting power out of batteries that are in the high plains. It's getting power out of wind and solar that are remote. So this is less a discussion of exactly of commercially available stuff. If you listen to Eckhart yesterday, he's got a long list of worries, and we aren't trying to gloss over those. But nevertheless, this exercise we think is quite consciousness raising and saying, look, it looks like using GFM with sensible current ratings appears to result in significant incremental power transfer out of resource-rich areas. You can't just call up Siemens or anybody else and say, deliver a gigawatt of wind with these boxes that Matt and I are using. But the notion that, oh, just tell us what you need or you can't have it until you prove it's worth it, we aren't happy with that. This says there's a lot of money on the table, and we ought to get moving in that direction.
Okay, and let me skip over one to go to the anonymous. What, if anything, does this work tell you about writing grid codes for grid forming devices, and maybe offer an opinion about grid codes versus market mechanisms?
I'll take a shot at that quickly. I think we are it's too early for our level of institutional understanding of what we want these things to do exactly. That's enough said. I think it's too soon.
I think, I think Andrew Isaacs yesterday also said it pretty well in terms of, we want to be careful about not being overly prescriptive about how these things work, and really try to define it functionally. I think as engineers, we all strive to do that, but it's a very serious challenge to do that well and do that right. I think that we're on our way to understanding the functional behavior, but I think to Nick's point, we're still very early. This is still very much emerging, and if you try to be, and particularly, you can really step in it if you try to be too prescriptive too early on.
Okay, I'm going to take the next three questions kind of together because they're related. On the grid strength impact slide, a question about models. Would you be willing to share the models you use so others can also analyze them or play with them? And then Julia's question about what type of control was used for the GFM virtual synchronous machine droop control. Would it have any difference in the general findings? And then a related question of how much of this is just theory versus real world, i.e. are the insights translatable to a real system?
Okay, great. Yeah, a lot of questions. Quick one on the modeling one. So the model is using black box models that are considered proprietary. So this is not open source stuff. This is not stuff that we can share. So sorry, Andrew, about that one. But that said, it's the double-edged sword that you have, because we did this because we wanted these to be as realistic as possible. And I think that plays to that last question in terms of, how much is this translatable? So yes, this is a desktop study. This is not, these plots that we were showing were exclusively simulation, not field test results, but we do feel that that this is translatable. I mean, the whole, reason for PSCAD models and high fidelity EMT models being developed by manufacturers is such that, the industry has confidence that they are translatable in the real world. So to the extent that we personally and much of the industry has that confidence, yeah, I do think it does translate. Now, there's another aspect of, the tools and the analysis and how to do that, right? And that's probably, we don't have time for maybe necessarily that discussion, whether you need to model the world in EMT at 20 microseconds or if there are other approaches. I think, in short, we're of the belief that there are other approaches too. And a note on, Julia's question. So in part, we have some suspicions about the types of controls, but we don't know. So I'm not really going to comment in detail about the details of the GFM because it is a black box model. But would it have any difference in general findings? Yeah, the broad blanket is, don't forget, these are software defined. And, this is just, if the software changes, the control can change, the behavior can change. And I think that's something that, we have to just be very aware of and careful with.
Charlie, you're muted, maybe?
Oh, okay. Can you hear me now?
Yep.
I think maybe I got muted because of the interference on my end. So maybe one last question on the models. I think there were a couple questions. I don't see them right now at the moment about the models that you used and their validity for the short circuit ratios that you used. I think it was, were they phaser models or were they EMT models?
Let me answer that because I can see a couple on here. So this is the only results you've seen today are EMT, PSCAD. The models are OEM models, best in class. You know, models are models. Models aren't hardware in the loop, so they have their limitations. But yes, we think that we made a conscious decision to use OEM models so that we could say this is something real. These are not sort of you know, generic models. Somebody on the screen here is asking about the clearing time. So in those stoplight charts, we did a lot of our cases at 100 millisecond clearing. These are EHV transmission lines, fully modeled, distributed parameter with compensation. So there's some natural frequency that feeds into the next person's question about weak grid and other, right? So clearly the natural frequency of the grid is another piece of the grid strength. We don't have series compensation. We did a bunch of tests where we were supporting that midsection with shunt capacitors, right? Rather than, and we didn't talk about that today, the behaviors, particularly with the GFM, were exactly as we would have expected. That lowers the natural frequency. That's a term in this grid strength. We got behaviors as expected. Is this general? Does this cover every possibility? Not on our lives. We absolutely aren't saying that, but we actually, somebody said, is this real or theory? Well, you know, these are the kinds of models that the industry has used to move forward for half a century. Yeah, this means something. Is this a real power system? Is this the specifics of somebody's power system? No, but we think these findings should help guide and help you look for things like these modal interactions. Are you going to see the same modal interaction that we found here? No. Is there going to be modal interaction that is complicated? Absolutely.
Okay, on that note, I think we're going to have to wrap it up now. We're about at the top of the hour, and we'll get answers to the rest of the questions that weren't responded to out in the next couple of days, hopefully. Nick and Matt, thank you for a very informative and educational presentation. I think there's something in there that we can all take away from it. I also want to encourage you to send any follow-up questions to info@esig.energy, and we'll get them answered along with the others and posted as quickly as possible. We really appreciate your engagement, and for those of you who have not yet had their fill of inverter-based resources, I invite you to tomorrow's ESIG session on the advent of the inverter-based system at 3 p.m. Eastern. All are welcome. Further information on all of our webinars can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Nick and Matt, thanks again for this very timely and fascinating webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thank you, Charlie.